Okay, so we're going to talk about example 11, but before I talk about example 11 and the rest of the examples from this chapter, I want to talk a little bit about proof. So how do you prove something scientifically? It's an open question. Most things that we consider scientific facts, we haven't really proven yet. We assume we have evidence, but they're not proven. A good example would be global warming, right? Global warming, there's a lot of evidence. There's this overwhelming evidence, but there's not proof in the mathematical sense, because you can't prove it in the mathematical sense. Usually there's this back and forth where somebody collects data and says, okay, I've collected this data. Based upon this data, I believe this to be true. Somebody else will come along and collect other data, and that contradicts it. Oh, that's, my data was different from yours. Or somebody comes along and says, okay, I accept your data, but your conclusion is wrong because you didn't take into account this, this, this. And there's a back and forth, and that's supposed to be the scientific process, right? This back and forth between experts in the field who've been doing the research. So yeah, that is the scientific process. Math is different. Because in math, we can 100% know what is true and what is false, because we've all agreed upon the rules of reality, right? We all know all the rules of reality. In the physical world, we don't know all the rules yet. We're still figuring things out. In the mathematical world, we can simplify the rules enough in order to know what reality is. But in order for me to prove something mathematically, or for somebody else to come along and disprove what I'm saying mathematically, we have to have a very precise language for laying out our claims. That is predicate logic. That is where predicate logic really starts to become very strong. Now, take a deep breath. Don't worry, in this class you won't be doing much in the way of proofs. This is not a math class in that sense. But I want you to understand that's why the rest of the examples in this chapter are mathematical examples. Don't get too caught up in the math portion, right? We're just saying, we just need to use that in order to have something to state in predicate logic. That's the only reason we're using math. So if you don't understand the math portion, and it's not strictly, don't worry about it. You're not going to be tested on any of the mathematical claims here. I just want to give you some examples of translating math statements into predicate logic, okay? All right, let's take a look at example 11. Okay, now example 11 starts getting into the concept of twin primes. But before we get into the concept of twin primes, let's talk about the definition in terms of predicate logic of infinitely many. Now, how do we say infinitely many in predicate logic? Oh, and I'm pretty sure I misspelled infinitely, but don't worry about that. Well, if you think about it, one way to say that there's an infinite number of something is that if you ever find, for any number you pick, I can pick one more, right? That's greater. As long as I can always pick one more that's greater, then there must be infinitely many. So we write that out for all m in the set of, in this case, we're going to use our set of natural numbers here. That's supposed to be a natural number n, right? For all m in n, there exists n, that's a member. You know what that is. It's a set of natural numbers. There exists an n in a set of natural numbers such that n is greater than m. So that's how we say infinitely many in terms of predicate logic. And then afterwards would go our, whatever our function is would come afterwards, right? Such that that function is true. So no matter what m you pick, I can go past that and find an n for which that is true. If I can always find one more n, then there must be infinitely many of them, right? So that's how we say infinitely many. Let me go back here. I forgot the most important part. For all m in n. I said it, but I didn't write it. For all m in n, there's some n that's greater than m for which the statement is true. That means there must be infinitely many. All right. Knowing that, let's get into the concept of twin primes. Okay, so let's move my misspelled definition over and let's talk about twin primes. Let's say that our function s of x is that x and x plus 2 are prime, right? That's our statement. Now, if we wanted to be correct and propositional, which we do, we would probably rewrite that as x is a member of our set of primes and x plus 2 is a member of our set of all primes, right? So that's a perfectly valid propositional statement. But we want to bring this into the predicate world, right? We want to make a predicate statement based upon this. And what our statement is that there are an infinite number of twin primes. So we did show before in our earlier example that there are some twin primes, right? 3 is a twin prime, 5 is a twin prime, but then 7 is not. So it's not that all primes are twin primes, but we're saying there are an infinite number. So how do we say there are an infinite number based upon this definition of infinitely many and this definition of twin primes? That's the question. What we would say is, for all m that exist in the set of natural numbers, there exists some n in the set of natural numbers such that n is greater than m and s of n is true. And in this case, when I'm using this s of it, that is referring to this up here, right? That is that function. So I'm saying for all m in n, there exists some n greater than m such that both the n and n plus 2 are prime. Now notice I'm not using the set of primes here. I don't need to because that is inside the definition of s of x, right? So I don't need to restate that these are primes. And the set of natural numbers includes the set of all primes. So primes is a subset of the natural numbers. And then this is often written kind of with a shorthand for all m in n exists n greater than m such that s of n is true, right? That would be perfectly acceptable on an exam because and although you really should make your greater than symbol cleaner than I did. But other than that, that would be acceptable on an exam, that kind of shorthand. We leave out the such that quite often, as long as it's understandable. So yeah, that's the twin prime conjecture. Are there an infinite number? We assume so. What I'm not getting into in this example is the negation of this statement, which they do get into in the book, and I do want you to read that. But for purposes of the lecture, I don't think that's strictly necessary. All right? If you have any questions about twin primes and infinitely many, ask in the forums below.